So we're working with buffers, day 2 essentially. Okay, our quiz was on acidosis actually, but let's take a look here. So what we're going to really work on today is more on buffering capacity. What is the effect on the buffer, right? If we add a little bit of strong acid or strong base, when the pH is going to change a little bit if you add some strong acid. It's not going to change as much as it would if the buffer wasn't there. But what will the new pH be? Or how much acid can you add and the pH would be that, right? It's kind of like going back to this acidosis problem, right? Like how much Coca-Cola could you drink before you really get in trouble here, right? You can almost, that would be a good question, right? That'd be a good one that this would work on. Okay, so there's 2 types that we're going to face of buffer problems. We might have a known amount of strong acid or base that's added to the buffer. What's the new pH? Kind of a trick right there in the beginning, right? You don't know whether that strong acid or strong base is being added, or how much of a particular strong acid or base is needed to adjust the pH to a specific value. So you know what the buffer is, but you need to add an acid or a base to it. So there's some pre-work we got to do before we can even work these. But essentially what we're going to do is make a mole table. And then we'll plug in our results into here. Okay, make a mole table. Of what? Well, we'll write a little reaction of what's happening. Like if we're going to add an acid, well, then we'll have a little H plus our conjugate base, our buffer, and we'll make a little mole table, what's going on, just to keep track of stuff so we can plug them into our equation. Okay, and where do you get pKa? Table or something, or Google it, right? Okay, let's see if we can play this game here. Let's take a look at the first one. How many mils of 0.289 molar nitric acid or 0.320 molar NaOH should be added to 128 mils of 0.0078 molar ethylamine to give a pH of 10.673. Okay. And I wonder if I have it. So Javier, how do we know, what is this doing here? Right? You'd think the question would just be like one or the other, not even have one of these, right? But no, you have to figure out which one you're going to add first before you can even work the question. So what can I ask you here? You're starting out with 128 mils of this concentration ethylamine. So ethylamine, you pull it off the shelf, measure 128 mils of it. The question comes down to, is ethylamine, remember the names? How do the names of these buffers go? The neutral name always corresponds. The neutral name, right? The name always corresponds to the neutral form. And how do you know whether the neutral form is an acid or a base? The structure need the table, right? So, and I don't have it. Do you have it, Javier? Look at the last class period. I scanned some of those. Man, you guys were doing so good. Did you do good today? Did you bring your book? All right, I know what's in here, but I don't know if it's in that. Maybe it is. Ethylamine sounds familiar, Daisy. In the last class period, you didn't bring your book. Oh, for shame. Oh, but I added it, so it wouldn't be in your book anyway. You found it? Yeah. Okay, he found ethylamine. So, Zach, does the name ethylamine correspond to the conjugate base or the conjugate acid?
Responds to the yes, it responds to the conjugate base.
I hear both of them. Let's take a look. Where are you at?
Right here.
Okay, it's on the bottom.
It's got an extra H, so ethylamine has to be the conjugate base.
Ethylamine. It's got that plus sign on there. If it didn't have that plus sign on there, right? So if it didn't have the plus sign, it would be the acid. But since you got to look really careful. It's got that little plus sign on it. No, let me write it down. Yep.
So in that structure there, is that referring to ethylamine or is it referring to a conjugate form of ethylamine? Because that does have a charge, not neutral.
Okay, hang on. I'm going to just write down so we can all be on the same page here. And I'm going to make this like in the book. They got this big, ugly blue, right? 3+. lost my color. Anyway. Okay. So this is what it looks like in the book. Oh, we need the pK before I give it back and I answer your question. pK 10.673. Okay, so you're going to have to be given this kind of information to work on these questions. Now, Zach, what's your question?
Okay, so you said that it's named according to its
Neutral form.
Okay, that's not a neutral form.
This is not neutral. So how do you make it neutral?
You remove an H.
Remove an H plus.
Right.
So that means that this must be the conjugate acid form. The conjugate base form is the neutral form.
So are you in solution? Is that going to be?
So in solution, this 128 mils of 0.078 molar ethylamine, that's all conjugate base. There you go, Victoria. Exactly. That's what I'm leading at. So you have to figure out, okay, the name is always a neutral form. Look at the table. It's a conjugate base. The neutral form is. That means, Victoria, you have to add the nitric acid because right, a base is going to react with a base. So you have to add. It implies you must add HNO3 to adjust pH. I mean, you could add base, but then you're going way outside of its buffer region because you're all at conjugate base form now. You want to get where you have a substantial amount, a substantial population of conjugate acid and conjugate base, so that it can do its buffer job. So you could add base, but that's just going to make the solution really basic. Go way outside the buffer region, kind of like that quiz. You remember that? Where is that? Where did it go? Here it is. Right? You add base, and you're just going to be way down here. Go further down. You're way outside the buffer region. It ain't going to work. The question wouldn't even be realistic then. Okay. So we're going to add HNO3. So let's get the big picture here first. We know we're going to use Henderson-Hasselbalch. Hey, instead of writing conjugate base all the time, what's our little notation of writing a conjugate base? A minus. That's going to be, even our little tables, I think it'd be easier. I think if we did that, maybe we do that today, that might help. Let's try it. Okay. So we're going to get our moles from our mole table. We got to make it. pKa we'll have, right? We'll look it up. We have that one. The pH, they gave us that. Okay. So we're going to use the Henderson-Hasselbalch equation to help us get our answer here. So let's make a little mole table. I'm going to have ice. But what's my reaction that I can make a mole table out of? I was just thinking, because Victoria said you had to add H+, or nitric acid. Well, you could write HNO3, but H+ is really all you really need. H+, plus, what's really happening here? H+ is reacting with the conjugate base, and we could write CH3, CH2, NH2, or just write A minus, right? Because that's our conjugate base, right? A minus is equal to our conjugate base. Okay? And that makes HA, the conjugate acid. Okay? So do we have there anything there initially for our, you can even kind of help yourself out. This is our first mole table for this. This H+ is from what? From the HNO3. Okay. So do we have anything there initially from the HNO3? Right? We just dumped in 128 mils of 0.078 molar ethylamine. Right? You haven't added any HNO3 yet, so there's nothing there You haven't added any HNO3 yet. It's initial, right? You haven't dumped any in yet. Okay. Do we have any initial conjugate base? Yeah. Now what number do you put there? Do you put the 0.0078 or do you put the moles? You can go about this two ways. Now remember, if you go about the traditional Henderson-Hasselbalch way, where these are concentrations and not moles, you got to take volume into account. And you can make a concentration table, but it's so much easier just to make moles because volume cancels out anyway. It's all the same solution. And then we can substitute numbers directly from our mole table into our modified Henderson-Hasselbalch. It'd be a lot cleaner. It's a little more work up front because you have to calculate moles to put in here. But I think it's worth the effort. So let's get the moles of the conjugate base, right? How would I get the moles of that stuff? Javier, how would I do that? How would I get the moles of that ethylamine? You remember? Yeah, volume and the concentration. Because remember, big M, Javier, what was big M again? It was what over what? Moles over liters, right? So just multiply it by the liters. Okay, so pretty much 0.128, I guess I could write it right here, 0.128 liters times 0.0078 big M. Okay. Do I have any initial conjugate acid there present? That's 100% conjugate base. We took that ethylamine bottle, right? Assume it's pure, I guess. Nope. Okay. Change. What do you think we should put in for the amount of H plus we're going to add? X. Makes sense for X or minus X? I guess it really doesn't matter. It's X, right? Because X is going to be the amount. Because this is really all this is it's just to help keep track of stuff. But I guess minus X because it's really reacting up right away. It kind of sounds odd to say it's a negative moles of H plus, but it works. Well, I think it's negative because of what we want to write down here for the equilibrium amount, right? It's going to be this moles, and it's not going to be plus X. It's going to be minus X because that's going to react. So I think it's kind of helpful to write what someone said, write a minus X, even though it looks weird. Nothing or minus, right? But does the H plus even show up in here? No. All we're interested in is this number and this number. That's all we're really interested in, because that goes in the Henderson-Hasselbalch equation. Okay. And then for the HA, we'll put X, because it's forming, positive X. So equilibrium row, just add stuff up. 0.128 times 0.0078, about 9.984 times 10 to the negative 4. 9.984 times 10 to the negative 4. Okay? Oh, I forgot the minus X part. And then just substitute everything into our Henderson-Hasselbalch, and now we can finally solve for X. All right. Something like, oh, we know what the pH is. They said it was 10.673. Has to equal the pKa, which is 10.673. Right? Plus the log moles of.
This is different than what we have in our book.
What does it say in the book?
10.78.
Sorry. Okay, let's change that. Yeah, something else is happening otherwise. Oh, but that's right though. 10.78. Okay. Plus the log of mole, let's see, conjugate base over conjugate acid. So I need the 9.984 4. Thanks for straightening me out there. 10 negative 4 minus x all over x. Okay. Now, I've never done the math to see if I can cheat on this and drop the x. I've always solved them out the long way. So if someone wants to cheat and drop the x and see what you get, then we'll compare it to the way. Let's solve it. So how are you going to solve for x here? I suppose bring this over to the other side. Raise both powers, raise both sides to the what power? To the 10. Solve for your x. I think it does make a difference. You're going to be off by, how? 100% if you don't. I haven't divided by 2 yet. So shift 1 over times 29. I got about 4.4 times 10 negative 4. Did you get that? See, so I have to bring the x over here. Then I have to add x to both sides. Right? So I'm going to pretty much add a 1x to it. That's why I'm thinking you can't drop that x, because it increases this number almost by 100%. So don't drop that. So bring the x up to the top. Right? That'll be multiply x times both sides. You'll end up with 1.279x equals 9.984 times 10 to the negative 4 minus x. Add x to both sides. You end up with 2.279x equals 9.984 times 10 negative 4. Okay? Jamie, slap him. Right? And then solve for your x. I got 4.38 times 10 to the negative 4. And that's units of what? What is my x? It's moles of what? It's moles of what? So go back to your ice table. It could be moles of HA, yeah. It's 4.38 times 10 negative 4. We want to know, in the end of this, we want to know what? How many mils of that nitric acid? X is the moles of H. That's the way to look at it. The moles of HA isn't really going to help you, right? But X is the moles of H+. No. What's your answer is how many mils of 0.289 molar HNO3 can be added. So we're close. We're really close. Yep. So multiply both sides by x. You get 1.279x equals this.
Plus x.
This is minus x right here.
Oh, yeah.
Right? So you have that times x equals this minus x. Right? 1.279 times x equals this minus x. Add x to both sides, that becomes 2.279 equals that number. Then just divide.
So this becomes 2.7?
Yeah, don't you have an x there.
Right.
You have to add an x to it. So do you see how to finish this? This is the moles of H plus. How do you convert moles of H plus to volume? Use what?
Wait, why do you have to give them
Because they want to know how many mils you can add. That's the final step.
to do it with the HNO3 concentration?
The HNO3 concentration. You know that you have 4.38 times 10 to the negative 4 moles of H plus. And then just remember what big M is. Big M is moles over liters. But we have to flip it. 0.289 moles of H plus in a liter. Did they want the answer in milliliters? Yeah, they did. Convert it to milliliters. Okay. Okay. About 1.52 or so is what I came up with. Okay. So back up a little bit here. How did we solve this? A lot of the homework is pretty much just like this. Right? You first figure out what the buffer is. Because the buffer is always going to be the conjugate acid or the conjugate base. The name. The name always corresponds to the conjugate acid or the conjugate base. One or the other. You look at the table and you figure out which one it is. Is it the conjugate acid or the conjugate base? If it's the conjugate base, you have to add HNO3. If it's the conjugate acid, you have to add the strong base. Okay? And then you make a little mole table, right? Identifying, oh, in this case, it's a conjugate base, ethylamine is, so I'm going to have to add H plus. Forms a conjugate acid. So you don't have to do this. I kind of do it because it helps me to keep track of these numbers. But you figure out the moles of your conjugate base that you had in the beginning. You know it's going to be minus X because it's going to react with the H plus. So you end up with the original moles of the conjugate base minus X. Okay? And whatever conjugate acid you form, that's going to be, what's 1 to 1? If you add 1 mole of H plus, you can get 1 mole of conjugate acid. So it'll just be X. And then substitute it into your Henderson-Hasselbalch and work on solving for X. All right, so we subtracted both sides from 10.673, raised both sides to the 10 power, ended up with this expression, brought the X over to the other side, multiply both sides by X, end up with 1.279 times X equals that expression. Add X to both sides, so I really ended up with 2.279X equals that number. All right, solve for X. And then you got to realize, oh man, what was X again? You got to go back. I go back up here, right? Oh, X is the moles of H plus that I added, because that's what I called my X in the first place. X is the moles of H plus. It's also the moles of HA. Yeah, and that makes sense because the amount of H plus you add, that's all going to convert it into conjugate acid. But so X is the moles of H plus. Easiest way to look at it, because they're after volume of H plus. Sorry, they're after volume of the conjugate acid that you added. So I started with my X, took a time, or I divided it by the concentration so the units would work out, converted into milliliters, got the answer. Okay? Okay. Write the chemical reactions whose equilibrium constants are Kb and Ka for imidazole and imidazole hydrochloride. Okay. So we're going to have to find those if you got a book. I should have scanned it. I didn't get to scan those. It's silly meeting kind of messed me up. Okay, on page AP15 is where imidazole is. Okay. Let's do it a different color. And the book also gives you 6.993 is the pKa. So on page AP15, I found this information. So Eustacio, what's the hydrochloride doing here? What the heck are they naming this for? Imidazole and imidazole hydrochloride. Or even imidazole. Which one is which? How are they naming this stuff? All right. Did anyone see what they're trying to do here? Maybe don't worry about the hydrochloride right now. Start with the imidazole. Right? The name always corresponds to the neutral form. It's going to be the base. This one will be our A minus. You could pull out a bottle of imidazole hydrochloride. That's going to be the conjugate acid. But do you see why they need to call it? Because you want to pull out a bottle of this stuff. The conjugate acid is not neutral. So that's what the little chloride is doing on there, right? It actually looks like that. So you can pull out a bottle of this stuff and get the conjugate acid, hydrochloride, imidazole, or you can get the conjugate base, imidazole, because that one's neutral. That's what the chloride is doing on there, okay? It wants you to write the Ka and the Kb reactions for these. So the conjugate base is imidazole. Take off the H, make it neutral, and write the Kb reaction. This is the conjugate acid, write the Ka reaction. All right, try it. Christina, how would you do this? All right, so let's write those. The Ka reaction, the Kb reaction. Right? Mariella, how would you write the Ka reaction? What would you write first? Imidazole hydrochloride guy, exactly. Goes to would go to imidazole. So now you just remove that H plus is all. That's what they wanted. Yeah. So you, just writing the HA goes to H plus A minus isn't going to cut it. Because they wanted you to write the Ka and Kb reactions for imidazole and imidazole hydrochloride. So you have to write it all out. I guess you could. Yeah. The table gives it to you in this format, though, so it'd be a lot faster just to copy what the table gives you. I think, but otherwise you got to be counting carbons and hydrogens and everything. All right. And then the Kb reaction. Conjugate base, all right, which is just imidazole, what we just wrote over here. And I'm so sloppy with writing these things. All right. God, that's horrible. All right. Hydride Kb reactions, the conjugate base plus H2O makes my conjugate acid. Good. Okay. Oh, I forgot. Plus OH minus. Okay, so there's our Ka and our Kb reaction. Does it make sense? So the table is, use the table as your big guide. Just figure out what's what. And the chloride is there just to make the compound neutral. If it's not neutral, you can't put it in a bottle, right? Okay. Calculate the pH of a solution prepared by mixing 1 gram of imidazole with 1 gram of imidazole hydrochloride and diluting to 100 mils. Shelby, you have an idea how to do that? They want the pH of a buffer, so probably just use well, the first one we added an acid or a base, and that's coming up in part C. But it's similar to the first one. They want the pH of a buffer. So whose equation do we use? That Henderson guy, right? Still think it's a lot easier to stick with moles. You don't have to. You can use concentration because they told us the volume. And we're going to need Monica's chemical formula. They don't tell you in here. You got to count up stuff. Well, we can count it up. Okay. So how you can get the moles of A minus? Albert, how are you going to get the moles of A minus? The moles of the conjugate base? Well, mole bridge is really converting from one compound to another one. This one would just be molar mass, right? Because they told us that we have 1 gram of, which one is the conjugate base again? Imidazole. So just convert 1 gram into moles. Put that up here. The hydrochloride, same thing, right? So we're going to need that chemical formula that I think Monica was talking about. I could get a better structure. This one has a better structure. Let's put our H's on there. 1, 2, 3. This one has an H, right? There's an H there, and there's an H there. So we're going to have 1, 2, I count 3 carbons. Correct me if I'm wrong here. And then this is for, I'm doing imidazole. Imidazole. I count 3 carbons, 1, 2, 4 hydrogens, and 2 nitrogens. Does that look right? Okay. And then the imidazole hydrochloride, imidazole, bless you, hydrochloride, it should be the same thing, but we'll just add what? Add the HCl, hydrochloride, so add the HCl. Oh, really C3H5 and 2Cl. So we need to find the molar mass of both of those. Convert them into, so we can convert our 1 gram into moles. About what, 68? Right. About 0.0147 grams of the imidazole. Correct me if I added something up here wrong.
So that's 68.
That's supposed to be a 68. It's hard to write way down there. So how did I get the 68? Right here. Add it up. Okay. 3 carbons, 4 hydrogens, and 2 nitrogens. Hydrochloride. Ah, thank you. It's the whole point of doing all this. Okay, so 68 plus 35.45 plus 1. I got about 104.5 about. About 9.574. Okay, so I'll just substitute those guys in. Get your pH, right? You looked somewhere what the pKa was, 6.993. About 7.18 about. Okay. Okay. Does it make sense so far? So we're just finding the moles of the conjugate acid, moles of the conjugate base, dividing the two using Henderson-Hasselbalch, because they told us the grams. In part C, okay, now find the pH if 2.3 mils of 1.07 molar perchloric acid is added. Oh, you had a game plan. Matt, you have a game plan? Will we use Henderson-Hasselbalch again? Ice table. They're asking for pH of a buffer system. So if you write out Henderson-Hasselbalch, an ice table might help, but maybe not. Maybe you don't need it. Right? The moles conjugate base over the moles conjugate acid. Do we know the original moles? Right? Do we know the original moles? Yeah, then we just get them. Okay. And we could make little mole tables, but if you add, what type of acid is this? Strong. Strong. It has to be strong, otherwise this is going to be a real mess. If they give you a volume and a concentration, do you know the moles? Yeah, right? You just multiply them. So you know the moles of H+. So let's say it's, I don't know, 0.01, just, or it's making up some number, whatever it is. Would you add or subtract that number right here? Is it going to increase it? Or is it going to decrease it? The moles of the conjugate base. It's going to decrease it. It has to, because that's the whole idea of the buffer. It's going to react with this. So we better have a minus sign up on top. The conjugate acid, is that going to increase it or decrease it? Or no effect? We're going to add some acid. You said that it was going to decrease the moles of conjugate base. That makes sense because it's going to react with it, right? But buffers, they react, right? The conjugate base reacts with it, and the conjugate base turns into the conjugate acid. This one has to be plus. is that number going to be the same? If 1 mole of A minus reacts, I'll form 1 mole of HA. So these numbers have to be the same. What is that number going to be? I don't know. Maybe I can't do this in my head. This. That's my moles of H plus. 2.461. All right. That's in milliliters. So whatever that number is, you know what the original is. So subtract it, add it, take the log of it, add to the pKa, find pH. Okay. Okay, so there's, it just keeps going on from there. We have about 1 minute though. Let me finish this. This is the last part. And it's kind of a trick question. How many milliliters of 1.07 molar HClO4 should be added to 1 gram of imidazole to give a pH of 6.993? Right? That's right at the pKa. Ah, my goodness. That's right at the pKa. Right? If you want the pH to be right at the pKa, Henderson-Hasselbalch isn't going to work. You just have to realize, I want exactly half to be in the conjugate base. I want half to be in the conjugate acid. So pretty much, you add enough to react with how many grams of imidazole? 0.5. Then you stop. Okay? So that's how you work out part D. At least that's how I work it out. Because I recognized, oh, this is right where pH equals pKa. So I'm at the center of the buffer region. That means the number of moles of A minus exactly equals the number of moles of HA. So add enough HClO4 to react with half of the imidazole. And that's where you stop. Okay? So we're about out of time. Mm-hmm.
So can I take the exam on Tuesday? On Wednesday, as I get back to
Oh, we have an exam on Monday already? Maybe you're right.
You guys are interviewing Friday. I leave Friday, so I'll be here that day.
Oh, okay. So yeah, you can take it either when you get back or
Okay.
before you leave. Yeah, it is coming up fast. Yeah, it is coming up fast. Yep.
Class this morning, can I take the quiz now?
For general?
Mm-hmm.
Yeah. Yeah. Just got to clean this up. Yeah, when you get back, it's fine. Will you get back on when? You get back when?
Tuesday evening.
Tuesday evening? Okay, then I can't hand the exams back.
From last week. And the
Okay,
lab I did
all right.
separate.
Oh, you did separate, so this isn't late then.
Yeah. Oh, also,
Yeah?
I didn't go on Friday because we had this other game.
They said they'd have it fixed by 2:30.
Yeah?
And so, but do you have the test? 'Cause
Yeah, you have to go to the office.
Okay.
You have to go to the office. Okay, We have to go to the office to get your quiz, Shelby. How come everyone's so tired in here today?
Well, I got sick, so I've been throwing up. That's
Really?
That's why I'm tired.
You guys look dead in here today. The extra hour, you should be super awake. No?
You didn't make it to class, did you? Are you still in advanced OChem? Anna was the only person that made it to class this morning.
Really?
She just texted me, yes. And I was like, I'm gonna try.
So there's a lot of tired